Thanks very much for being here. I'm Daniel. I'm going to talk about shape morphing sheets. So as a disclaimer, this is going to be another one of the talks where, so I'm a postdoc here currently. This is older work because it fits the theme a bit better, but it's still work where when we did the work, the focus wasn't really on frustration, but the system is frustrated, and hopefully I can give some takeaways which are still of broad interest to this audience. And so I'm going to talk about liquid crystal elastomers, LCEs. Thankfully, Hillel's basically done all this for me, so I'll skate through it quite quickly. So these are synthetic rubbery solids, and when you activate them, that means heat them up or shine light on them or do various other things. They undergo these large, spontaneous, anisotropic deformations. And so the picture, if you have a unit cube with a molecular director that's all one way, and you heat it up, you activate and you contract by this factor that I'll call lambda parallel along the director, and you expand by this other factor lambda perpendicular in the other two directions. So here's a very old video now of, actually it's a 10-frame video of how these work. And so you turn the heat on, it was a hairdryer in this case, I believe, and the thing contracts because the director is vertical, and then you turn it off and it reversibly goes back down. And so you might be able to tell from that picture that that was a thin sheet, and Hillel, as we saw, started to break out of this paradigm, but we usually think of thin sheets in these systems, and I will restrict to that. That's partly because they bend easily, and so they can do cool shape changes. And I'm also going to restrict to the director being in plane as drawn, and so then the picture is just like the 3D one, except like this. So you contract again by lambda parallel this way, and lambda perpendicular orthogonally, and you don't worry about what's in the other direction. And the director doesn't need to be uniform and boring. It can be patterned. You can do things, for example, via photo patterning, as shown here. So these are through cross polars. So the brightness is a proxy for director. And the point here is that you can do incredibly intricate things. And also with 3D printing these days, you can basically make any pattern you want. And so then you can make interesting patterned in-plane deformations. And because of Gauss, that morphs flat sheets into curved sheets. And so then you can program, quote unquote, interesting, cool, complex shape changes, which people are excited about for soft machines that you control just by things like heat or light. And so what kinds of things have people done in this area? Again, you already saw some of this. And so, for example, concentric circles patterns make cones. In the bottom left, you see that these cones are absolutely spectacular. So you heat them up and they can lift hundreds, sometimes actually thousands of times their own weight, which is pretty astonishing. You can make spherical caps and saddles and other wavy things. This is from Hillel and others. There's a whole series of kind of more intricate or general shapes, whole series of faces. You can do all kinds of things these days. And it's not just LCEs, and so various kind of biological tissues, the math is very similar, and various other synthetic systems. My favorite are these inflatables where you make a pattern of air channels and then pump air into them. The thing that's cool about these is that they can be big, and so two of these have kind of moderate scale bars, but you'll see in the last picture here that the scale bar is Emmanuel Siefer, who is actually quite tall, so this is very impressive. So I already showed you this picture, so this is how do we think about these theoretically. So each tiny piece wants to do this when you activate, and you can encode this behavior in a preferred metric tensor, A bar. So metric tensors describe distances between neighboring points, and it has this funny looking form that Hillel already showed, but it just is another way of writing what's in the picture. And then the realized metric, A, the actual metric, may not be the same as A bar, and these deviations cost stretch energy. But there's also, if these things morph into 3D, there's some curvature tensor, which we call B, and these things want to stay flat. And so there's some bend energy that depends on B. And overall, the shell minimizes an elastic energy that looks in cartoon form like this. And so there's a stretch term proportional to thickness that penalizes these deviations, A minus A bar. And then there's a bend term that wants to stay flat. B here is curvature. That's proportional to thickness cubed. And so why are these frustrated? I don't usually include this slide, but I thought for this audience that would be worth doing. It's probably familiar to many of you. And so why can you not just have E equals 0, so A equals A bar, and B equals 0? And the short answer is because Gauss says so. And the slightly less short answer is that Gauss says that the Gauss curvature, K, can be calculated intrinsically just from this metric A bar. And so if I give you some general A bar and you calculate the Gauss curvature, it will just be non-zero. And that's incompatible with this bend energy that wants to be flat. And just as a reminder, so the Gauss curvature is just the product of the two principal curvatures, which are the curvatures of these arcs. And so if you confine one of these things to the plane and don't let it curve, you get huge frustration. Buckling out of plane into curved surfaces partially relieves frustration, but not completely because of this incompatibility that I mentioned. So Gauss curvature is clearly key for shape and also for mechanics. And so we should work out how to compute it. And so if you parameterize this director in the plane with a polar angle psi, you can crank the handle on a formula from hundreds of years ago, and you get this messy expression for the Gauss curvature. So it's a big kind of nonlinear bundle of second derivatives of the director field. And then there's this prefactor that depends on the lambdas. And the main thing I want to point out about this, which is not kind of maybe immediately obvious, but we can see it fairly clearly, is that it has a kind of neat property. And so there's an operation you can take, which we call the orthogonal dual. And so one way to think about that is that you rotate the director by 90 degrees everywhere in the plane. Another way to think about that is to keep the same director and just interchange the two lambdas, same thing. And what you can see from the prefactor here is that, thinking about it in the lambda way, when you do this, you just flip the sign of k. You just get an overall minus sign, nothing else happens. Okay, so remember that. Okay, so now what about topological defects patterns? So I already showed you this pattern on the left that makes a cone. And so this, when you activate, tries to contract azimuthally and expand radially. And it turns out you have to make a cone to do that, something isometric to a cone. A cone has 0 Gauss curvature along the flanks, but the tip looks like a tiny little spherical cap. And so there's a concentration of positive Gauss curvature there. When you take the dual, to get radial director, you get something called an anticone, which has is again Gauss flat everywhere, except it has an anti-tip that looks like a little saddle with concentrated negative Gauss curvature. And what may be vaguely familiar is that the integral of Gauss curvature you can think of as an angular deficit. So it's actually a solid angle on the sphere that the normal vector traces out. And so hopefully you'll believe me that in the cone case, you can calculate this quite straightforwardly, basically from trigonometry. You just need to work out the cone angle. And you do that and it pops out to be this thing. And what you'll see here is if you take the dual to go from left to right, you swap the two lambdas, and again, the sign of k does change, but also the magnitude changes. The sign, it's not just a sign flip, the magnitude also changes. And so this means that this behavior is fundamentally out of reach of this smooth formula that I showed you. This formula just cannot capture that behavior. And it doesn't matter how careful you are with, these patterns are non-smooth, but it doesn't matter how careful you are with, derivatives of delta functions and all kinds of magic you might try and play with. Like this prefactor just means that it can't be doing the right thing for these kinds of patterns. Topological defects and other non-smooth patterns. And so what do? We turn again to Gauss and Bonnet. And so we use the Gauss-Bonnet theorem to calculate the total amount of curvature. And the Gauss-Bonnet theorem, if you're not familiar, is basically a divergence theorem for Gauss curvature. It says that if you want to compute the total amount within a patch, you can just compute a loop line integral around the boundary of the patch. That's of this other thing, kg, which is geodesic curvature, which is another intrinsic thing that you calculate just from the metric a bar. And this is nice, because if you have some topological defect patterns, for example, like in the top right, you can take a loop that encloses the defect, and all around that loop, the director is smooth and nice, and there are no singularities of any kind to worry about. And then you can just crank the handle and work out the total amount of Gauss curvature inside. And when you do that, another handle cranking, you get a formula that pops out that looks like this. And so it has a first term here, which we call a structural term, which depends on the bend and the splay, B and S here, and again on some bundle of lambdas. And then there's this extra term, which is a topological term, which is proportional to the topological defect charge M. Okay. And so this gives you the topological term here gives you a quantized ladder of enclosed curvatures, and you can test this numerically. So here, the colorful lines are numerics. We simulate these different defect patterns, what they minimize the elastic energy, and evaluate the Gauss curvature in ever larger regions. So this is a function of radius. And you see that near the origin, near the center of the defect, bend is going crazy. And so you're far from being an isometry of A bar. But as you go further out, you become isometric and you asymptote to this topologically quantized ladder of charges, which is kind of cool. And the activated shapes are also very pretty. They do all kinds of funny things. The different charges, I really like this one in the top left because the pattern has 6-fold symmetry. When you minimize energy, it breaks that down to 3-fold symmetry, which is kind of cool. And some of them don't even stay rotationally symmetric. They're very kind of weird, interesting things. And I'll mention also, since Hillel mentioned it, so Hillel showed us that in 3D, even with smooth director patterns, you can get this cool non-monotonic evolution of curvature, whereas you just dial temperature up, say, you go from being, the intrinsic curvature starts from 0, goes to non-zero, and then goes back to 0, so you can end up happy. And this shows that in 2D, you can't do that with smooth patterns, but you can do it with non-smooth patterns. And that's, again, similar to his formulae, coming from the fact that you have multiple terms, and they have different lambda dependencies. And so at non-trivial values of lambda, they can cancel. to 0. And so in this case, for example, you make a cone so you start with a flat disk, you increase the temperature, you get a cone, and then it goes back to a flat disk at a higher temperature. So again, non-smoothness, really different. Another thing you can do is think about line discontinuities, where so the director is doing something funky across a line interface rather than just at a point. These also yield singular Gauss curvatures, concentrated Gauss curvatures generically. And again, you can crank the Gauss-Bonnet handle, and that saves the day. These are LC experiments, and you get these sharp Gauss curved ridges with these sort of rather biological looking shapes. And you can use these for actuators, they're strong fingers. And again, you can calculate the Gauss curvature with Gauss-Bonnet theoretically. That's the red line on the left, and the black line is numerics. And again, it all works out. And on the right line, you see again that if you compare a pattern and its dual, again, the sign of Gauss curvature flips. This is plotted along the ridge line. Again, the sign flips, but it's not just that the sign flips. The magnitude also changes. And so again, the smooth formula is just, there's no magic you could do. Like it's really fundamentally different. The smooth formula just fails. And then these can get even weirder when you join patterns together. I just like showing these with curved interfaces. So Mark Warner was part of this work and always referred to these as tortured cones. It's a sort of step beyond frustration, I guess. And they have amazing mechanics and it's endlessly fascinating to us anyway. And so the kind of takeaways here, I haven't really told you about mechanics very much. This was mostly geometry, but the point is that these differences with the smooth case are also there in the mechanics, because near these singular features, the stretch and bend terms in the energy are comparable, even in the thin limit. Stretch and bend are fundamentally trading off, and so the kind of frustration compromise that's going on is fundamentally different to the smooth cases in the thin limit. And that can have extreme, even kind of extreme macroscopic global consequences in some cases, which I can talk more about offline if people are interested. And so the takeaway is that if you have a frustrated system where the frustration parameter in some sense is in some way patternable, I would urge you to think about non-smooth patterns of frustration, because it can bring genuinely kind of new surprises and novelty. And I will stop there. Thanks very much.
Questions?